So let's start. First concept you should know is scalar field. Scalar field is a function of is a scalar valued function of position. For example, temperature as a function of x, y, and z is one example of a scalar field, or you could have height of a hill as a function of x and y. That would be another example. Vector fields are very similar to scalar fields, but instead of having a value as a single scalar, they would have a value as a vector, so they would have 2 or 3 components depending if we are in 2D or in 3D. Example would be electric field as a function of x, y, and z. Since electric field is a vector, it would have x, y, and z component. I'm not actually sure if you've seen electric field before, but it has 3 components. Another concept you should know is position vector. Position vector is a vector that gives a position of a point. So if you have a point with some x and y coordinates, the position vector would be equal to x coordinate and y coordinate put into this sort of a vector. It would be, if you were to sketch the vector, it would look like this. And you can also write it in terms of this I vector and j vector, or we also will use x hat and y hat. In 3D, same idea, but now you also have a z component, or you could call it k, or you could call it z hat. Here are some scenarios in which you'll encounter position vectors. One is when you want to describe a contour. To describe a contour, you could define a parameterization variable. Here it's called t. This variable t could have some bounds, or it might go from negative infinity to infinity. In the example I'm showing here, let's make it go from t1 to t2. So in this case, x, y, and z components would depend on t. And when you make t equal to t1, you are going to have some point. Given by r of t1. And then when you sweep t from t1 to t2, you are going to describe the entire trajectory. So your x, y, and z are going to change until finally you arrive at a point given by r of t2. This I'm discussing the 3D version, but you could also have 2D, same situation, but now you will not have any z component and only x and y. You don't have to parameterize in terms of some generic variable t. You could also parameterize in terms of x. In this case, when you vary x, your y and z change depending on what x is. In both of these situations, position vector is a function of a single variable. So, and that is why you describe a trajectory. Now, if you want to describe a surface instead of a contour or just a single trajectory, you would use 2 parameterization variables, u and v, and then your the components of the position vector would be functions of u and v, or you could use x and y as parameterization variables, and then z would be a function of x and y. So then when you sketch this up, as you vary x and y, there will be corresponding value of z for every point. So you're going to describe the entire surface. So this would be your position vector, either at x and y or some more generic parameterization variables, u and v. Now, why are these these quantities useful, this position vector as a function of t or position vector as a function of u and v, you will use it, for example, to find tangent vectors to contours or to surfaces. So here, to find tangent vector to contour, what you'll do is you'll differentiate the position vector with respect to the parameterization variable, and this is going to give you a vector that is tangent to the contour. If you want a vector that is a unit vector that's tangent to the contour, you would divide this guy by a magnitude, by the magnitude of this. So you will get t hat unit vector that is equal to this divided by the magnitude of this. To sort of wrap your head around why this vector is tangent to the contour, you can imagine an analogy where t is time. It doesn't have to be time, but let's just imagine for a second that it is time. And you know from physics courses that derivative of position with respect to time is velocity, and velocity always goes in the direction of the trajectory. That is why tangent, at least in the case when this is time, this vector would be tangent to the contour. There is a more rigorous explanation for this, but it's kind of to understand why it makes sense. And then for describing surfaces, you will do a similar thing, but now you'll differentiate with respect to either one of these variables, and you'll learn how to do it a bit later. Next is linear independence and basis. Let's review linear independence. Here, what I'm asking is which of these sets of vectors are linearly independent. Let's start with the one on the very left. This one, you see they are not linearly independent because A is a scalar multiple of B, or you can say B is a scalar multiple of A. These two vectors are linearly independent, so this would be yes, because there is no way to write A as a linear combination of B or B as a linear combination of A. Here, they are not linearly independent because C, for example, can be written as a linear combination of A and B. So you could write, say, K1A plus K2B, where K1A would be this, say, no, K2B would be, for example, actually just this, and K1A would be this. Here, they are linearly independent because there is no way to write C in terms of A and B, or A in terms of B and C, or B in terms of C and A. A basis is a set of linearly independent vectors that span the entire vector space. I haven't told you what vector space we're talking about, but once you define a vector space, you can talk about basis for this vector space. So when we say that three vectors v1, v2, and v3 are basis vectors, what we mean is that any vector in the vector space can be written as a linear combination of these three vectors, where a1, a2, and a3 are some scalars. An example of a basis would be x hat, y hat, and z hat, because any vector in three-dimensional space can be written as a linear combination of these three x hat, y hat, and z hat. So then we say that these three vectors form a basis for R3. This basis has some special properties. First, it's right-handed. What do we mean when we say right-handed? When we sketch x hat, y hat, and z hat, if we align the thumb with the first vector, x hat, by the way, the order matters. So let's imagine you align the thumb with this vector. Align the index finger with y, and then your middle finger then would be aligned with z hat or be in the direction overall of z hat. Now, right-handed system doesn't have to have z hat sticking up like this. If z hat were in this direction, say, it would still be right-handed. As long as it's not pointing down, it would be still right-handed. Oops. This system is orthonormal, meaning that the unit vectors, or to say, sorry, the basis vectors are perpendicular to each other. And each of these vectors is a unit vector, so the magnitude of each of the basis vectors is 1. Now, the reason it's called right-handed is because you're using your right hand to get this. If you check and try to do this with your left hand, you're not going to get the middle finger aligning in this direction. So let me just draw how this looks like with your right hand. So your thumb points in this direction, your index finger points in this direction. Imagine this is your palm sticking up. Then your middle finger is going to be like this. And then this is the rest of the 1, 2, 3, 4, 5. Yes, this is the right hand rule. Now I want to mention that if you swap any two of these, you are not going to get a right-handed system, you will get a left-handed system. So first, let's swap, let's say, x hat and y hat. So you get y hat, x hat, z hat. Order matters, by the way. So then you'll get y hat is this way, x hat is this way, z hat is this way. Let's incorrectly use your right hand, but this would be wrong. So imagine, so I'm going to write right-handed with a question mark because we don't know if it's right-handed. So y hat is in this direction, this would be your thumb. Then you go with x hat, this would be your index finger. And then the right hand's middle finger would be going downwards. So for this to be a right-handed system, you would need to take negative z hat instead of z hat. So this, as is not a right-handed system. So I'm going to erase this because it's not right-handed. Right-handed guess was incorrect. This is actually a left-handed system. Oops. So now imagine left hand's thumb aligned with y hat. Left hand's index finger aligned with x hat. And then the left hand's middle finger would stick upwards, which is in the general direction of z hat. Now, again, the reason I'm saying general direction of z hat, because it's not, it is aligned in this case because z hat is perpendicular to y hat and x hat. If it weren't perpendicular, that's still fine as long as it doesn't, as long as it's upwards and not downwards. Okay, now if we swap again any of these two, then you'll again get a right-handed system. Let's swap x hat and z hat. So, because x hat and y hat is not very interesting because you'll just get back this. So let's try y hat and then z hat and x hat and check that this would be right-handed. So y hat is this way. This would be thumb of the right hand. Z hat is this way. This would be index finger of the right hand. So then the middle finger of the right hand would be in the general direction of x hat. So this would be middle. Now, this was an example of one of the ways to write basis for R3. This is not the only choice of basis. Any three linearly independent vectors in R3 would form a basis for it. So you can write any vector in terms of some alternative basis. And for two-dimensional space, it would be any two linearly independent vectors. For example, you could choose some v1 like this and v2 like this. Oops, that's crooked. And write any vector as a linear as a linear combination of these two vectors. So this would, for example, a vector like this would be formed by elongated version of this guy. We don't know how much elongated, that's why I'm drawing a dotted line. And then elongated version of this guy. So you see this would be some scalar multiple of v2. And this is also a scalar multiple of v1. So you don't have to write everything in terms of x hat and y hat. There is alternatives. Now, there will be several different coordinate systems, so several different choices of basis vectors that you'll see later in the course. One example is cylindrical coordinate system. Sorry, not cylindrical. This is polar. Polar coordinate system. This is in 2 dimensions. The basis vectors for it are r hat and theta hat. Here's how they are defined. Let's imagine you're at some point right here. R hat would be a vector that points away from the origin, and theta hat is a vector that points counterclockwise along this circle that I've drawn here. So then any vector that you imagine can be written in terms of theta hat and r hat. Here, just to warm up, I'm showing you the opposite problem. I'm giving you linear combinations of r hat and theta hat, and I'll ask you to draw this. So let's do it. Well, I'll draw it because unfortunately it's not an in-person class. So, okay, so here I want to draw 2 r hat. This would be a vector like this. Here I'm drawing 2 theta hat is a vector like this. And here is r hat plus theta hat. So it would be a vector like this. So here is a problem of having a linear combination and being asked to draw it. But you could have an opposite problem. You could have any vector, just whatever vector you could imagine that starts at this point. And you could write it in terms of r hat and theta hat. I also want to talk about notation that's used a lot in reading assignment 3. So suppose that we write a 3D vector v in terms of a basis that we chose, n1, n2, and n3. These could be just x hat, y hat, z hat, or some other vectors. So we write it like this as a linear combination of the basis vectors. Then if you can represent these basis vectors as these column vectors like this, being 1, 0, 0, and 0, 1, 0, and 0, 0, 1. If you do that, then this v is equal to this guy. Let me highlight everything that's the same. So you would have v1, this v1 times n1. Then you'll have v2 times n2, and you'll have v3 times this third basis vector. As I'm talking, I just realized that v before meant a vector, but it can mean a scalar. Now vectors are n and scalars are v, so just don't be confused. v3 times n3, so then you have this, this, and this. Okay, so if you write it like this, if you added the way you normally add matrices and vectors, you see here you'll get v1, 0, 0, plus 0, v2, 0, and 0, 0, v3. Adding these three matrices or column vectors together, you'll get v1, v2, v3. That's one operation you should be comfortable with, and you'll see it, I think, quite a lot. Another way to write this, which again you'll see in the reading assignment, so I don't want you to be confused by this, is like this, in this matrix form, where you'll write, instead of this sum, you'll write it in matrix form. So you'll have this v1 times this column, v2 times, oh, and let me highlight it here as well. So this would be n1. You'll have v2 times this column, so n2, and v3 times n3. This is just the way matrix multiplication works. If you don't feel comfortable with this, what I suggest you do is you take several matrices, just take a 3 by 3 matrix and a column vector, and multiply it and convince yourself that it's the same thing as taking columns, multiplying them by these coefficients in the column vector, and then adding the three things together. So this is nothing more than just the way we multiply matrices. And I don't remember if reading assignment 3 explains it or it assumes you know it, but just I want to give you a heads up when you're reading. Okay, next part is different operations between vectors, which I think you should know. I'm pretty sure you know scalar product, or also known as dot product. It's defined, or you can think its property is that if you take one vector u, another vector v, then the dot product would be given by this scalar here, which is equal to the magnitude of the first vector, magnitude of the second vector, times cosine of the angle between the two. So this would be theta uv. And if you write each of these vectors in terms of Cartesian basis vectors, you can expand it like this in 2D. This would be your u vector, and this would be your v vector. You can write it in terms of x hat or y hat, or you could write it in terms of this triangular notation. And then in 3D, you would have one more component, z hat, here, 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 and here. Here, what I'm showing you is a 3D version of the dot product. 2D works the same way, just doesn't have z hat. I'm showing you, so I'm expanding u hat in terms of the Cartesian representation, and then do the same thing for v hat. Then you get a whole bunch of terms. I'm using a distributive property of the dot product here. So I'm taking these products with x hat here, like this, and like this. This would be this row. So you see ux, vx, x hat dot x hat plus ux, vy, x hat dot y hat plus ux, vz, x hat dot z hat. Then here is the same thing, but with y hat. This is this term. It has uy, vx, and y hat and x hat. Then same thing here. Again, uy, y hat, but now we have vy and y hat plus this term. You'll have uy, vz, y hat, and z hat. And then the last one is this. Let me highlight the green one so you have it in your notes. It's this one. And then the blue one. Okay, so we have uz, z hat, uz, z hat, uz, z hat. And now we have a dot product with vx, x hat, vx, x hat, vy, y hat, and vz, z hat. So this is how you'll expand it. You can do it, I'm essentially skipping a few steps here because you can first break this up and then take a dot product, but I'm just getting to the answer. Now, we know that x hat, y hat, z hat form an orthonormal coordinate system. What does it mean? It means that x hat dotted with y hat, for example, is magnitude of x hat, magnitude of y hat, times cosine of the angle between the two. So this would be 1 times cosine of pi over 2 because it's orthonormal. And cosine pi over 2 is 0, so we get 0. Same way we get 0 for all the cross terms. Sorry, well, I mean for x hat, z hat. So this would be 0, 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 and this would be 0. So we're just left with these guys. Now, we also know, again, because of the orthonormality, that x hat dotted with x hat equals to 1 times 1, because we're dealing with unit vector because of orthonormality. So this is 1. Same way for y hat. So these guys are just 1. Maybe I'll write like this. 1, 1, and 1. So for 3 dimensions, we will end up with just ux, vx, uy, vy, and uz, vz. And for 2 dimensions, same thing, but without the z part. Now let's talk about vector product or cross product. It's defined like this. This guy is a unit vector that gives direction of this cross product. This part gives you the magnitude of the cross product. Magnitude of the cross product is magnitude of one vector, another vector times sine of the angle between the two. So this would give you this. I'm actually going to make this u, and this would be v. And this would be theta uv. The reason this is interesting is because of this. V sine uv is this. This is V sine uv. So what you have is this times this, which gives you the area of the parallelogram. If you continue this guy and this guy, if you multiply this height by this base, you're going to get the area of this guy. Now, what is this n hat? N hat is given by the right-hand rule. How you'll get it? You'll align your thumb of the right hand with the first vector, index finger of the right hand with your second vector, and then the middle finger, the direction of the middle finger, which would be perpendicular to this and this, would be n hat. So in this, for example, case, this would be thumb, index finger, so thumb, index finger, and then the middle finger would stick out of the page. And all of this with right hand. Don't use your left hand, use your right hand. Okay. Now, in Cartesian representation, you can, if you write components in terms of x hat, y hat, and z hat, you can compute the cross product by getting a determinant of a matrix like this, where you will write u, so that your first vector here, and the second vector would be here. And here you'll write the unit vectors. So here, let me compute this determinant. You will get uy vz minus uz vy times x hat minus y hat times this determinant. You'll have ux vy minus uy vx. And then the third one is z hat times this determinant ux vz minus uz vx. Now the reason you can do this, this computation, is because the Cartesian basis vectors form orthonormal system, which is right-handed. So both properties are important. if you have a system that's not right-handed or not orthonormal, this wouldn't be a valid computation. And in the reading assignment section 3.3 of reading assignment 0, there is a proof of this. Now, I just want to give you a heads up. I think I swapped U and V compared to the reading assignment notation, so just follow through from the beginning if you want to understand the proof. Next part is the scalar triple product. Scalar triple product is defined by cross product of the first two vectors, and then you take a dot product with the third. It's also invariant under circular shift. It means that if I take this vector and sort of pull it out to the left here, and then B sort of drags along with it, and then I take C and it shifted over to the right, then I get the same value of the scalar triple product. Same thing happens here. If I take B and shift it over to the left, C drags along with it, and then A goes to the end, again, same value. Now, this should be volume. So, scalar triple product has some absolute value and it has some sign. Absolute value of the scalar triple product is equal to the volume of the parallelepiped that's formed by these three vectors. Let me explain why. First, let me draw the parallelepiped for this case. And then I'll draw the one for this case. So for this one, we have A cross B, which is equal to, okay, so let me write C dotted with A cross B. A cross B is equal to magnitude of A, magnitude of B, times sine of the angle between the two. This would give you times n hat, where n hat is a vector given by the right-hand rule. This part, no, okay. So then let's take a dot product between C and N. So you'll get A, B, sine theta AB, and then C, N would give you magnitude of C magnitude of N is 1, because remember it's a unit vector, times cosine of the angle between N and C. So this is what the scalar triple product equals to. Now, this part is equal to the area of the base of the parallelepiped. This we just discussed when we talked about cross product. This is the area of the base. This part, C cos theta and C, in this case, N hat and C hat are in the same overall direction. So this is a positive number since the angle between the two vectors is, I guess it's smaller than 90 degrees. Theta and C. And this guy is equal to the projection of C onto N hat. So this is that. And this gives you the height of the parallelepiped. So you see we have base of the parallelepiped times height of the parallelepiped, which gives you the volume of the parallelepiped. Now, this quantity is already positive, so absolute value of the scalar triple product is the same as just the value of the scalar triple product. So in this case, scalar triple product is positive. How about this guy? Let me sketch the parallelepiped for this case. We have this, 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 and this, and then this and this. Okay, so in this case, this is equal to what? We have C hat dot product with absolute value of A, absolute value of B, times, well, actually the same thing. You see, this calculation didn't really depend on anything on the direction of these. So actually, in this case, scalar triple product is for this and for this, it applies. But in this case, this red part still is area of the base, and the difference comes in this part. So here, n hat is pointing upwards as before, but C is pointing downwards. So n hat is still this way, but C is pointing downwards. So this angle is greater than 90 degrees. So this dot product is negative, which makes the overall scalar product a negative quantity. But if you look at the magnitude of this, you know that the absolute value, then you know that if you look at the let me make it blue. If you look at the projection of C onto this, then what you'll get is magnitude of C times, well, not cosine of this angle because cosine is negative, but you'll get absolute value of cosine of this angle. So then you know that if you were to take absolute value of this, so this would have absolute value, the cosine, then you'll get the volume of the parallelepiped. You'll get the height times the area of the base. But because this quantity is negative, you are going to get volume of the parallelepiped, but with a minus sign. So to conclude, absolute value of this, so this guy is the volume of the parallelepiped, and the sign could be positive or negative. Now, when is it that the sign is positive and when is it negative? The sign is positive when A cross B points in the overall direction of C. So in other words, A, B, and C form a right-handed triplet. A, B, C form right-handed triplet. And here, C points down instead of pointing in the same direction as N. So here we have a left-handed triplet. where left-handedness and right-handedness is the same as we just discussed when we talked about basis vectors. Now, these guys don't have to be basis vectors for anything. Well, they are, because they're linearly independent in this case. But right-handed and left-handed concept applies no matter whether we talk about basis vectors or not. Now, if this guy is 0, it means that C points, it means that this projection is going to be 0. So C would be in the same plane as A and B, which would mean that it's neither right hand nor left hand, but it would be linearly dependent. So there is only 3 options depending on the sign of this. So if it's right-handed, then the sign of the scalar triple product is positive. If it's left-handed, then it would be negative. And if it's 0, then, and if it's not linearly independent, so it would be linearly dependent, then the sign is 0. Now let's do some questions from 13.5. This is question 44. It asks you to find an equation of the plane that passes through the point 2, 3, 0 and has a normal vector -1, 2, -3. As you should have seen from reading 13.5, equation of such a plane that passes through a certain point, x0, y0, z0, having a normal vector like this, ABC, is given by this equation, which essentially says this. Let me first draw the normal vector, n. It says that the dot product between the vector, between the normal vector and the vector given by x minus x0, y minus y0, z minus z0. So this would be a vector going from the point x0, y0, z0, and the head of the vector would be at a point x, y, z. It says that for every point on this plane, this dot product should be 0 because the two vectors are perpendicular. So you see it would be a dot product between A, B, C and x minus x0, y minus y0, and z minus z0. So then using this formula, we can easily get the equation of this plane. So we would have our normal vector this, and this. This would have components. This would be your A, B, and C. Let me also highlight this and this. And this would be x minus 2, which I got from this, y minus 3, and z minus 0. So this would give us this vector. And these terms, well, factors in this dot product. So then we just need to expand this and simplify. So we get, here we get negative 1x plus 2, then plus 2y minus 6, then minus 3z, and then 0 disappears. Then we can add 6 on the two sides of the equation. So this disappears, and here we get plus 6. We can subtract 2 from both sides of the equation. This cancels this 2. And then we're left with negative x plus 2y minus 3z equals 6 minus 2 is 4. And then we can remove this one because it's not really doing anything. Let's do the next question. This would be number 49. This question asks to find an equation of the plane passing through the points P103, Q042, and R111. This problem doesn't give you a normal vector, but you can find the normal vector. Here's how we'll do it. We have 3 points. We have a point P, we have a point Q, and we have a point R. They all lie on this plane. By looking at the vector PQ, vector PR, and taking a cross product, we will get a vector that's perpendicular to this vector and to this vector, because remember, cross product is perpendicular to both of the original vectors. Sorry, I actually drew this incorrectly because I should use the right-hand rule. So PQ, align your right-hand thumb with this, index finger with the second vector. So then the normal vector that will be given by PQ cross product with PR is going to give a normal vector. So this problem reduces to the previous one. We have normal vector, we will have normal vector through the plane, and then any one of these 3 points can be used to get the plane. So let's do this. Let's find PQ. So we would subtract position vector associated with the final point Q. We would subtract position vector associated with this point, 103, and we would get -1, 4, and -1. For PR, we would get position vector associated with R minus position vector associated with P, and we would get 0, 1, -2. Then we take the cross product. Let me actually use just this. So we have PQ given by -1, 4, -1, this one. We have PR that I copied here. And then we need to find this determinant. Again, this works because we are dealing with a right-handed orthonormal system. First, we would find this determinant. We'll get I hat and then 4 times -2 minus -1 times 1. Then we have minus j times times this determinant. We have -1 times 2 minus -1 times 0, so that's just going to be 0. And here we have k times this determinant. So we get -1 times 1, and this guy will give us 0 because of this one. So we get I times -8 plus 1. that would give us -7. Here we have -2, but then with this negative it gives us +2. No, something's wrong. Sorry. I made a mistake. This should be minus. Because remember we were taking this determinant, so we have -1 times -2, right? So then this would be +2, sorry. Okay. So then this guy would give us -2, and then k would have -1. So then we get this vector. -7, -2, -1. Now you can take this vector, or you can take the opposite of this as your normal vector to the plane, so that you don't have to deal with these minus, minus, minus. So taking -n, which is 7 to 1, as the normal vector, we can find the equation of the plane. Now there is 3 options. We can take either of the 3 points as our point that lies on the plane, and I want to show you that you'll get the same equation. The reason you'll get the same equation is because you've specifically constructed this. I mean, if you found the correct normal vector, no matter which point you'll use, you'll get the same equation. Or you'll get an equation that looks different, but it's actually the same. So let's use point P, which is 1, 0, 3. You see here I have components of the normal vector. So I have 7 to 1. And then I have this point, 1, 0, 3. Then I expand this. I get 7x minus 7 plus 2y, and then plus z minus 3. Then I added 7 and I added 3 to both sides, and I got 10 on the right-hand side. That's how I got this equation. If instead you use point Q, this would give you 0, 4, and 2. When you expand everything, you'll get 7x plus 2y minus 8 plus z minus 2. Then you add 8 and add 2, and then on the right-hand side you'll get 10. On the left-hand side you get the same thing as before. If you use point R, same thing. Have 1, 1, 1. And when you expand things, you'll get 7x minus 7 plus 2y minus 2 plus z minus 1. Then you'll add 7, you'll add 2, and you'll add 1. So this would give you 7 plus 3 on the right-hand side, which again is 10. And on the left-hand side, you have the same thing as before. So all these give you the same equation of the plane. But you don't have to do all 3 if we ask you. If we ask you to give an equation of the plane, you can just use this or this or this. Question 63 from 13.5. The question gives you an equation of the plane. It's x plus 3y minus 5z minus 30 equals 0. And it asks several things. One is to find points at which the plane intersects the coordinate axes. It also asks to get equations of the lines where the plane intersects coordinate planes. And it also asks to sketch the graph of this plane. Let's start with the x, y, and z intercepts. To find those, for example, x-intercept, you would set z and y to 0 and figure out what x is. So here I'm copying the equation of the plane. You see x plus 3, y minus 5, z minus 30 equals 0. But I'm setting y and z to 0. So I get x equal to 30 because these two are gone. So the x-intercept would be somewhere here. Y-intercept, same idea, but now we're setting x and z to 0. And y is the only thing that's left. So we get 3y equals 30, which gives us y equals 10. So the y-intercept is given by 10. Z-intercept, same idea, but we leave only z and set everything else to 0. So then we get negative 30 equals 5z after I transfer this to the right-hand side. So then dividing by 5, we get z equals negative 6, which is here. So if I continue this, I get z equals negative 6. So then the plane, we know that it goes something like this. So above this line, it would continue on upwards in this direction. So then I hope you're sort of imagining how this would go. So this, what I'm showing you here, is a portion of the plane that's made up of these 3 points. Now, the lines where the plane intersects the coordinate planes would be these. For x equals 0 plane, this would be the yz plane. We need to set x to 0, so we get 3y minus 5z equals 30. This would be this guy. Xz plane would be y equals 0. This would give us 0 for y, so we get x minus 5z equals 30 by transferring 30 to the right-hand side again. So this would be that. And then the z equals 0 plane, which is the xy plane, would give you z equals 0. So we get x plus 3y equals 30 by transferring this to the right. This would be this. Let's do the next question. In this question, you are asked to find a line of intersection between 2 planes. One plane, which is Q, is given by negative x plus 2y plus z equals 1. The other plane, R, is x plus y plus z equals 0. Let's do a quick sanity check to make sure they actually intersect in a line. There is, in general, 3 possibilities. One is that Q and R are 2 parallel planes. In this case, their normal vectors would be parallel to each other. They could be in different directions and they could have different magnitudes, but the main thing is the direction of the 2 vectors is going to be parallel. So this is the case NQ parallel to NR. If NQ is parallel to NR, you could also have the case where the 2 planes are identical, because there is no guarantee there is any distance between the 2 planes. Now, equations might look different, but let's say if one equation is a scalar multiple of the other equation, so you take this and multiply both sides by 2, for example, to get the other plane. then you'll have identical planes. So if the distance between the planes is 0, you'll also have this case. So this is this, and this one is like this. So that's one plane with its normal vector, and this would be the other plane. And the normal vector could be the same, or it could be in the opposite direction. Now I shouldn't really be saying the normal vector because there's infinitely many normal vectors, but you get the point. Okay, and the third case is when the two vectors are not parallel. If the vectors are not parallel, then the planes go at some angle, and if planes go at an angle, then they intersect in a line. Actually, this is what I'm showing here, so I'm not gonna draw it too carefully because I have a picture here. Okay, so let's check which case we have. For this, we need normal vectors. NQ, reading off the coefficients, would give us -1, 2, and 1. And NR is 1, 1, 1. And the question is, are the two things parallel? In this case, no, because for them to be parallel, you need one to be a scalar multiple of the other. But if you try to get from NR to Q, well, from first, component, you'll think it's K is -1, but then this thing doesn't work out because if you multiply 1 by -1, you'll get -1, but that's clearly not the right thing. So they are not parallel. One is not a scalar multiple of the other. So the answer is no, they are not parallel. This means that we have this third case. So the two intersect in a line, so the question is correct. The question is not asking us for a nonsense thing. Now let's find the line. First, let's find a vector that's parallel to this line. So we have two planes intersecting, and we're looking for a vector that goes in this direction. How we are going to find it, let me actually draw it like this from here, from this point. This is a vector in the direction of the line L. We are going to find this line by looking at the two normal vectors. So let's make this plane Q. Is this correct? Yes. So this is plane Q. It has a normal vector. Yes. A normal vector that points something like this. You see, I drew it perpendicularly to this pink plane. Plane R has a normal vector like this. Or it might be in the opposite direction, but that's not my point. Now, you see that the cross product of, R, of NQ and NR is going to be perpendicular to this vector. The reason why is because NQ is perpendicular to anything that lies on the plane, to any vector that lies on the plane, including this vector. So these guys form 90 degrees. And NR is perpendicular to anything that lies in this plane, including this vector, so it's perpendicular to this. There is, now, any vector that's perpendicular to this and this is going to lie on this line. And by finding a cross product between these two vectors, we're going to find some vector that's either going to be in this direction or in this direction. If we take the cross product in this order, the way I drew the picture, we're going to get NQ, so align your thumb here of the right hand and index finger here. So then the cross product is going to be in this direction, but the main thing is going to be on this line. So this is the cross product. Let's compute what it is. We have -121 for NQ. We have 111 for NR. So then we get, for I, we get this determinant, which gives us 2 minus 1. Then we have minus J, -1 minus 1. And then K, we have -1 minus 2. So we have 1, -2, and -3. So here we'll have 1. These negatives cancel, so we get 2, and then -3. So this would be a vector parallel to L, this black vector I drew here. Now let's find a point on the line. Let's call it P0. Now there is an infinite number of points on any line, right? But we can decide which point to take. For example, we can take, so let's imagine this line L goes something like this. It doesn't actually, but let's just imagine for the sake of discussion. And let's say it intersects. What we can do is to fix the point as the intersection between x equals 0 and the x equals 0 plane. So essentially I'm saying we don't know what x, y, and z are, but we have a freedom to choose at least one of them. So let's fix that x equals 0. So essentially we're finding the point of intersection between the line and x equals 0 plane. Now this is assuming the two actually intersect. So what I did is I copied these two equations, but I plugged in x equals 0. So I'll have 2y plus z and y plus z, and I'll have 1 over here. So it's 2y plus z, 1, and y plus z. Then we can solve it by this. Let's subtract the two equations from each other. Well, let me write q minus r. So we'll get 2y minus y gives us y. Z minus z cancels. This is equal to 1 minus 0. So we get y equals 1. So we have x equals 0, y equals 1, and now we just need to find z. For example, from here, we have z equals -y equals -1. So we have x equals 0, y equals 1, and z equals -1. Now in this part, let me continue and then I'll get back to this, what I want to say. Now, we found the point on the line and we have a vector in the direction of the line. Let me highlight those. So this is the cross product that we found, this black vector that I've shown you. And this is this point. Then for this, the vector equation of this line is given by position vector as a function of t is given by this point, position vector associated with the point P0 plus t times this vector. and t is any real number. So essentially, we're saying that when t equals 0, we are at a point, our position vector points to this point we just found. And then when t is positive, we are going in the direction of this black vector that we found. And then when t is negative, we're going in the opposite direction. And the larger t is, the longer this vector we're adding. So our position vector is going to go from the origin to this endpoint. And as a result, we'll end up spanning the entire line. So this is the position vector, r, as a function of t. And the parametric equations you would get by reading off the components of this. So the x component of the position vector is 0 plus t, so you get t. Y component is 1 plus 2t, this is what I got here. And z component is negative 1 minus 3t. Now, what happens if, you know how I assumed that this point of intersection exists, and we found it. So it does exist in this case, so there's nothing to actually worry about. What happens if the point of intersection doesn't exist? This is the case where your line is parallel to the x equals 0 plane. This means this could happen, for example, so if this happens, you will not be able to find this point of intersection, but you don't have to choose x equals 0. You could choose z equals 0 in this case. So you'll still be able to solve the problem. So this not a real problem. So if this happens, then set z equals 0. Now I just want to make a few comments on example 4 from 13.5. The question asks to figure out if two lines intersect, and if they intersect, then to find the point of intersection. Now there is, so the lines are given by parametric equations like this, and the parameter for L1 is t, parameter for L2 is s. Now each of those lines has a vector in the direction of the line. The first one, let's call it V1. It has components 3, 3, negative 1, which I read off from these coefficients. V2 is given by 2, 3, and negative 2. 2, 3, negative 2. Now, there is several scenarios that are possible. If these two vectors are parallel, it could mean one of two things. It could either mean that the lines are parallel, or it could be just the same line that's written in different way. So this would be the case where V1 is parallel to V2. You could also have, now if V1 and V2 are not parallel, there is also two scenarios. One scenario is when the two lines intersect. So it would be one line, and then the other line is like this, so there is a point of intersection. And you could have also in 3 dimensions a situation where these two lines don't intersect, right? In this case, they're called skew because they're neither parallel nor intersecting. So one line would go sort of like this. And then let's imagine, for example, the other line is above this one or below. Let's make it below. So this is like that. So they don't intersect. This would be skew. In our case, we can narrow it down because we see that the two vectors are not parallel. So we have one of these two cases. We don't know which one, but for sure the lines are not parallel and not identical. So let's figure out which one it is and at the same time attempt to solve for the point of intersection. So basically, if we're successful in finding T and S, then we found the point of intersection. If we can't find the values, then the lines don't intersect. So what we do is this. We want to find, we have this line L1 and we have the line L2. And let's imagine that they intersect at some point. If they intersect, this happens when parameter t for L1 is at some value. So some value of t, we don't know what it is. And L2 also has its corresponding value for s. Because remember, every value of t gives you a point on L1, and every value of s gives you a point on L2. So for L2 at this point, there is also some s that we're trying to find. And we want t and s to be such that x values are equal, y values are equal, and z values are equal. That's what it means for the two lines to intersect at a point. So what I did here is I copied this and this. I copied this and this. And I copied this and this. So we have now a system of 3 equations and 2 unknowns. In general, if you have a system of equations, there is several possible scenarios. So I'm not talking about linear equations necessarily, just some arbitrary system of a whole bunch of equations with a whole bunch of unknowns. You could have a unique solution, you could have no solution, you could also have multiple distinct solutions, and you could have infinite number of solutions. So those are possibilities. I can't think of any other possibilities, so this should cover it. But in this particular case, actually, we've ruled out some of these scenarios. We know that since we're talking about two lines intersecting, we know that, well, there is no way to intersect at multiple points. So we know that it's either no solution or infinite solutions if the lines overlap, or it's a unique solution, but it's not multiple distinct solutions. So that one doesn't work for our case. We've also ruled out a possibility of infinite solutions. The reason why is because we already determined that the lines either intersect or they're skew. So it's either one solution or no solutions. So let me recap. So this is because talking about intersecting lines. So intersections of lines, of two lines. And they can't intersect at multiple distinct points. Because it's straight lines, right? We can't, and this we ruled out because of this. Also, this system has 3 equations, 2 unknowns. In general, so if I gave you a typical scenario. So I just pick two random lines. They are not going to intersect usually. So in a random case scenario, or if I chose these coefficients kind of randomly, you would have these two equations give you some t and s, and then this equation, if I chose it randomly, there is no reason for this equation to be consistent with what this answer gave me. So when I plug in t and s from these two equations into the third equation, more often than not, this equation is not going to be satisfied. This would mean that there is no solution to the system, so lines don't intersect. But we can always we know that lines can intersect, so in this case, it could happen that this would be consistent with these guys. Now, in this particular problem, it turns out that there is no solution. So by solving, let's say, these two equations and plugging in the solution into this equation is violated. So this gives a conclusion that the lines are skew. But in a different part of this problem, this was part B, it turned out that the lines are actually intersecting. I'm not going to solve this problem, but it's just to help you understand how to do this. Okay, let's do question 60 from 13.6. But before we do it, I want to discuss a few things to make sure we're all on the same page. First, if we sketch a surface that's given in this implicit form, so some expression in terms of x, y, and z equals to 0, then if I instead sketch the same thing but with these coefficients, but by replacing x with coefficient times x, coefficient times y, coefficient times z, it's the same thing as sketching this surface but compressing x by a factor of a, compressing y by a factor of b, and compressing z by a factor of c. So it's the same thing as how if you graph, let's say, y equals x squared in 2 dimensions, and then instead you graph y equals 2x all squared, the graph would be compressed by a factor of 2. So whenever we have something sketched in terms of x, y, and z, multiplying x like this, replacing x with ax would essentially compress everything in the x direction by a factor of a. Next, I want to talk about sketching hyperbolas. Let's say I give you hyperbola like this, x squared minus y squared equals 1. First, we can figure out the x and y intercepts. To get the x-intercept, we would set y equals 0. So x-intercept is given by x squared equals 1, which immediately gives us x equals plus minus 1. Y-intercepts are negative y squared equals 1. This is impossible, so there is none. So we have x-intercepts given by plus and minus 1. And then, when we have x and y being very, very large, then we'll have, for example, y squared equal to x squared minus 1. But when y is very, very large and x is very, very large, well, let's talk about this one. If x is very, very large, then this expression becomes sort of like this. So we have y approximately equal to plus or minus x. So in the limit, as x approaches infinity, the two start sort of, your graph looks sort of like a straight line. So, and then for intermediate values of x and y, we have something in between a straight line and having this x-intercept. So that's how you draw a hyperbola. And then if I swap x and y, then you'll get the same thing but with y-intercepts instead of x-intercepts. Okay, so now let's do the problem. The problem asks you to match up different equations with different surfaces. Let's start with this one. This is essentially y equals z squared, and x can be anything. You see that this whole equation doesn't depend on x. This makes it as, it's called a cylinder, and it's going to be parallel to the x-axis. And essentially, you see this makes it look like a parabola if we fix x, and it's like y equals z squared, or maybe z squared times something. So you see that this makes sense with this one, and nothing else looks like it could work. So this immediately tells us that this is the one. This guy is an equation of a plane because you see there is this expression is linear in x, y, and z. You could even read off the normal vector of this, and you could figure out point on a plane and things like this. You see that the surfaces only have one plane. It's this one. So this determines that. Now we have this expression. This is sort of like x squared plus y squared plus z squared equals 1. Or we could write minus 1 equals 0. This gives us equation of a sphere. But we have these coefficients. Now, whenever you have coefficients, this is what I explained here. We are essentially just going to compress or stretch x, y, and z. So this guy gives us what's called ellipsoid. So it's like a sphere, but it's squished in some directions and stretched in others. This one. Let's figure out this guy. This would be what? This is parallel to the z-axis. The reason why is because when we change z, the picture shouldn't change. So we are either on the surface or not on the surface because x and y either satisfy this equation or don't satisfy, but z doesn't play any role. So we need to figure out which of those pictures is z invariant. The only one is this one because everything else has the picture change in z direction. So it's this one. And also if we fix z, for example, we'll look at z equals 0, we get this check mark looking graph, which is exactly the graph of y equals magnitude of x. Which ones are left? This one and this one. Let's start, for example, with, well, between this one and this one, we can figure it out by looking at this point. So here, 0, 0, 0 is a solution. And here it's not. So let's plug in 0, 0, 0. For this one, it's a solution because 0 squared plus 0 squared over 9 equals 0 squared is satisfied because we get 0 on both sides. So this should be that. For this one, if we plug in 0, we'll get 0 squared plus 0 squared over 9 minus 0 squared equal to 1. So then we get 0 equals 1, that's not satisfied. So this should be that one. Now, this, we could also figure out a trace, one of the traces. For example, we could set x equals 0 and sketch how that looks. So for this guy, just to have a sanity check, if x equals 0, then we have y squared equals to 9z squared. This gives us y equals plus or minus 3z. So when we look at the trace, we get, this is the trace x equals 0. And indeed, we get something that looks like y equals plus or minus 3z. For this guy, the trace when x equals 0 would be like this. If x equals 0, then we get y squared over 9 minus z squared equals 1. And this looks like an equation of a hyperbola, but with y stretched by a factor of 3. So then, in the x equals 0 trace, we should observe a hyperbola, which is exactly what we're observing. You see, this looks very much like what we just drew here, except instead of x and y, we have z and y. Well, y and z. And you see that we have y-intercepts, because if we set z equal to 0 now, we will get y squared over 9 equals 1, which has solutions. That's why y-intercepts exist. Let's do problem 79 from section 15.1. The question gives you this function f of xy equal to inverse sine of this quantity here, which is x minus y, all in brackets, squared. And the question asks to find the domain and to do two things, to specify it mathematically and either describe it in words or with a sketch. First thing I want to show you is how to treat sine inverse function. So I want to show you what domain of a single variable sine inverse function is, which you also call it arcsine. And I'm telling you that this domain is for the argument to be between -1 and 1. Let me explain why. Well, you can think there is sort of two explanations. First is this. What is the meaning of inverse sine? For inverse sine, you take this u, which is sine of some angle, and then the function returns this angle. So for this whole operation to be meaningful, u needs to be a sine of some angle, and sine of any angle is between -1 and 1. That's one explanation. Second explanation is this. Let's sketch sine inverse. Remember how we sketch inverse functions? We first sketch just a normal kind of a function, and then we reflect it with respect to the x equals y line. So let me first sketch sine. It would look something like this. Here we have 0, this is pi, this is pi over 2, this is negative pi over 2, this is negative pi, and then the highest value is 1, and the lowest value is -1. Now let's sketch the inverse function. So we're essentially swapping x and y here. Or you can think you're reflecting this guy with respect to this line, which is y equals x. So this would be a function y equals sine inverse x. So here now x maximum and minimum is going to be -1 and 1. The intercepts with this, with this axis are going to be pi and negative pi. Oops. So, okay, so when x was positive, y was positive, so we have the same thing. When y, now, sort of, let's say when x is 1, we're going to get pi over 2. So this point, for example, corresponds to this point. This is pi over 2. This is 1, and we have this chunk. And then on the other side, we have the opposite thing. So you see a point -1, negative pi over 2 corresponds to the point negative pi over 2, -1, this point. Okay, now you will also notice that this function, this is not actually a function because it would fail a vertical line test. So how to deal with it? People usually restrict the function to actually be like this, just this part. And then this part they remove. Okay, but why am I showing you all of this? It's because I want you to see that this function, inverse sine, is only defined between -1 and 1, this domain here. Okay, so what does it mean for this guy? It means that, that for this to be defined, we require that this guy is between -1 and 1. And nothing else can go wrong with this function because this part is just perfectly well behaved. So we're restricting this x minus y altogether squared to be between -1 and 1. This can be broken into two inequalities. First is this part, and second is this part, and they need to hold simultaneously for this guy to be true. Now we know that this part, saying that a square of something is greater or equal to a negative number, well, that's always the case. So this inequality is actually can just be removed. It's always true. Always true. So it's not really a condition that needs to be taken care of. This guy can be broken again into two parts. One is, sorry, not broken into two parts, but you know that if a number squared is less than or equal to 1, then the part before squared needs to be between -1 and 1, right? So x minus y needs to lie on this interval. Then when you square it, it's going to be between 0 and 1. So this is how I got this. Then the next thing I did is this. I took this one and I rewrote it as, I shifted y to the left-hand side. So I got y is less than or equal to, -1 goes to the right, so I get x plus 1. And here I got x minus 1 is less than or equal to y. So then this guy I just copied down here, and this guy, well, I just swapped the left and right hand sides. So x minus 1 with this guy flipped is here, and this guy is here. Notice how I flipped the inequality sign, obviously. Okay. So this is that. And then this is something that we can sketch easily. So we can write, so we can draw like this. We have, we need to draw a line y equals x plus 1. and a line y equals x minus 1. So this is y equals x plus 1. This is y equals x minus 1. And then y going between, which is less than this line and greater than this line, is going to be the one in the domain. And this is what I described here. Domain is a set of points x and y such that y is between x minus 1 and x plus 1. Now we could have stopped actually maybe here, or maybe here, say here, and written this condition instead in here. The reason why I went through all of this getting y to be separate is because I wanted to sketch it, because this part is a little bit hard to sketch, but this part is easy to sketch because I can just draw a line, the two lines, and shade the area between the two lines. Okay, so that's it for this question. Let's move on to the next one. Next is question 34 in 15.1. Here you're asked to match up a whole bunch of surfaces to their corresponding level curves. The way to draw level curves is to have, to graph your surface and then consider a fixed height, z0. So this would be some fixed height, z0, and looking at what happens at this height. You see here we have a circle, and then we project this circle onto the xy plane, and we get a shape like this, again a circle, and then this would be your level curve. Now this is for a particular height z0, and then you could change this z0 and get a whole bunch of these curves. You would want to change this z0 by the same amount, so you would change the height to be here, to be here. So you would look at all of those evenly spaced planes. You would look at what kind of shape you cut out. You would project all of these on the xy plane, and then you get the corresponding pattern. So these are exactly the patterns that are shown on this side. So we need to match up what we see here with the corresponding level curves. Let's actually start with the one I'm showing. This would be D. This one, you see there is a whole bunch of circles on the xy plane when you do this procedure. The only level curve drawing that has those nice circles is this one. You would also notice that these circles are evenly spaced, so you see radius kind of changes by the same amount. This you can explain by the fact that it's a nice cone. When you change the height by some amount, so let's say you go from here to somewhere here, your z changes by some amount and your radius changes by some amount. And when you look at your next surface, your z will change by some amount and your radius will change by exact same amount as it changed before. The reason why is because there is this nice straight line here in a cone. That's why the radius will change kind of evenly when you look at your different heights. Now let's look at this guy. This guy is similar to this one, but it has ellipses instead of circles that are elongated along y direction. The only thing that could have ellipses on level curves is this guy. Indeed, when you cut out z equals z0, you would get an ellipse. Then you project it on the xy plane. and you see it is elongated along y direction. You would also notice that these lines are not evenly spaced. Let's discuss why that is. Let's imagine this circle and let's say this, not circle, ellipse, these two ellipses. Those would correspond to some lower heights. So these are spaced by some delta z. And let's imagine these two ellipses. I'm not actually particularly good at drawing ellipses on a computer, so yeah, just imagine it's an ellipse. Okay, these two ellipses. So these guys are also separated by the same height. But you see their radii are going to be much more similar. So this kind of difference in radius is going to be much smaller than this difference in radius. It's kind of hard to see on the heights I've chosen, but you see here, this paraboloid starts off increasing this radius fast, while the height is not really changing much, and then slowly both the height and radius are changing, and then eventually you get to the point where your height is changing fast, but your radius is not changing by much. So that's why when your radius is not changing by much with the change in height, that's where you get those close spacings. So whenever you see this kind of closely spaced lines, that's where you have rapidly changing value of the function. That's where your function is either increasing very fast or decreasing very fast. And then those far away spaced lines mean that your function is not changing by much at these points. Let's look at maybe, I guess, this guy. This one, when we cut out a horizontal plane, we get lines like this, and then we project them on the xy plane. So you see they are horizontal lines where x changes and y doesn't. So the only option is this one. Again, we have a situation where slow change, slow change of the function gives you far away spaced lines. So this would be here, here, and here. And rapidly changing function gives you closely spaced lines. So this would be here and here. You see they're spaced. When you project them on the xy plane, they're going to be spaced very closely. Unlike these guys when you project them. Okay, now we're just left with we have this one and this one, which look kind of similar, and we have this one and this one. Let's determine which one's which. Now you see that, well, right away, this for sure is not this, right? So we're not trying to match these two guys to this one. So for this guy, if I set up my surface, my plane somewhere here, I get circle like this. So when I project it on the xy plane, I should get something where there is 2 points on the x-axis corresponding to the center of these circles. So these would be these 2 points, right? These guys are on the y-axis, not on the x-axis. So we know that this guy is for this. For this one, we have the opposite situation. We have our 2 circles on the different y values. So this would be probably, you know, this circle maybe and this circle. I don't know, I'm just choosing random ones. I haven't thought much through which circles that is. But anyways, this should be the correct one. Now this one is left only with this. Let's just try to understand whether this guy makes sense. Let's imagine cutting out somewhere for positive z value. Let's say here. My shape would be like this, the shape I end up cutting out. And when I project it on the xy plane, I should get something that has two x-intercepts, because they would be here and here, and then it would open up into positive and negative x direction. So this red part, which is the positive z, corresponds to something here. And then for negative z, we have a similar situation, just in the opposite direction, well, in the direction of y. So this shape would have 2 y-intercepts and would open up in positive and negative y direction. So this would be this. Now, looking at this graph, without seeing this, I wouldn't have been able to really tell how these how the level curves should look like. Well, maybe approximately, but I wouldn't be able to get this exact shape. But since I have this shape, I'm just trying to make sense out of it. I'm trying to understand, why do we have this kind of pattern? How could it make sense? And that's what I'm sort of showing here. Now, you see these 2 lines when this would correspond to z equals 0. And it would be somewhere sort of, if you imagine these guys just keep going, so this z keeps decreasing. You see, you kind of get closer and closer to the origin in terms of your lines. And then eventually these blue lines should sort of meet with the red lines. And that's what happens at z equals 0. But anyways, you don't really need to know this part to do this question. Just matching up was all that's required. But we should have some fun too.